Right. So let me repeat the big theorem we were proving last time. So there is an anti-equivalence from C to the field of rational functions on C, from the category of smooth projective curves to the category of fields capital K containing our base field small k of transcendence degree 1, and well, maybe this is the first point. The second point is that the inverse equivalence takes such a field to C. This is set theoretically the set of all DVRs. Well, let me call it RC in K, such that the fraction field of RC is equal to K. So this is set theoretically with Zariski topology, where the closed sets are the same as finite sets. And for an open set, the structure sheaf sections on this open set are just intersections over all points, well, so-called points in this open set, the corresponding DVRs. Okay. Now, the next part is that any.
Извините, а U это открытое подмножество множества всех DVR-ов, да?
Yes. So it's the complement from the set of all DVRs to the finite subset.
Спасибо.
So any smooth curve, say S, with the same field of fractions, rational functions on S, is an open subcurve S in this C. Okay. And this is the statement of the theorem. Now we started the proof last time, and we finished the essential part of the proof. So last time, yes.
Да, меня слышно. Это будет наивный очень вопрос про второе.
Yes.
Вот,
Yes.
вот точка в С. Это что? Это DVR.
Yes. And it's,
Одна точка в С это один DVR.
Oh yes. So this.
А как это? Так, точка же соответствует максимальному идеалу.
Well, to define anything at all in our mathematical life, we use the language of set theory. We first define some set with extra structure, right? So we first define the underlying set, then the topology, and then the structure sheaf. Okay, that's what I did, right? Well, conversely, this ring is the local ring of this constructed curve C at the point this small. Okay. Last time we constructed C with the structure sheaf, so as an algebraic curve, as the normalization of some projective line with coordinate T, a transcendental element in K. The normalization of P1 in the field of fractions in our field K. Okay, so
почему здесь важна трансцендентность? Вот, почему мы...
Well, otherwise T will be a constant, and there will be nothing to do.
Спасибо.
Okay. So we're almost done. What else do we have to check? To check the functoriality of the above construction. What do? We take a morphism of fields, so an extension of fields, a finite extension. And say our C is a set of DVRs in K. I mean, not all DVRs, but the ones whose field of fractions is K. Okay, and say S is the corresponding construction for this extended field L, and then our S is nothing but the normalization of the curve C in this extension of its field of rational functions. Okay, and point-wise, the morphism, the canonical projection of P from S to C takes a DVR, the RS in L to its intersection with the field K. Okay, and so this will be a DVR in K, whose field of fractions will be the whole K. So it makes sense point-wise. Okay. By the way, when I formulated this equivalence from the category of smooth project curves, then I should have said that we consider not all the morphisms, but only surjective morphisms, or maybe finite morphisms. So where should I add this? maybe here with surjective. That's the same as finite in this situation. Morphisms. Otherwise, if I project to a point in the base curve, then on the level of field of fractions, this will be just zero morphism. Not interesting. Okay. So yes, the question? No?
Yes, may I ask?
Yes. Yeah.
А вы можете на каком-то примере показать, как вот этот функтор работает? Берет поле и изготовляет из него проективную кривую, гладкую.
Well, somehow this was inside. This was hidden inside the proof last time. So I started. I started with the field just of rational functions like this, and the corresponding curve was just projective line with coordinate t.
Просто как проективная прямая может быть точки проективной прямой, каждая точка должна соответствовать какому-то DVR, какому-то кольцу.
Absolutely. Then any point C in here goes to the corresponding local ring. Okay, this is a subring in this field of rational function. Okay, and then any other field K containing this field of rational functions goes to some curve C, which projects to P1, and it is the normalization of P1 in K. Okay, we had this construction a week ago, and now we have applied it.
А если это поле просто К, вот не К, Т, а числовое поле?
Then it does not have transcendence degree 1. It's too small. So for a field to be the field of rational functions on a curve, it has to have transcendence degree 1. We had such an exercise last year, right? The dimension of a variety is the degree of transcendence of its field of rational functions. Okay. Here it is.
Спасибо.
Владимирович, а уже видно из доказательства или вот из этого примера, где вот проективность кривой важна для единственности конструкции?
No, not yet. We are going to it. So let's go straight there.
I'm sorry, last remark.
Yeah.
Over the first line, it should be written frac RS intersect K.
You mean here? Or where, once again?
Over first line, frac RS intersect K equal to K, because frac of RS is L. No.
Right. Yeah, maybe I should say, sorry. Okay. Here, yeah? Right? Yeah. Okay. So now let's go to projectivity. By what we know already, any rational morphism J from a smooth curve to our curve C necessarily extends and uniquely extends or maybe I should sorry. Sorry, maybe let me denote a little bit differently. From U to C, and it is smooth and it is contained. So let me call this P, and this U is contained. Sorry. In S, which is smooth. Okay, extends uniquely to P hat from S to C. Yeah, so we have such a diagram. We had an embedding U into S. There was a morphism P to C, and then there is an extension like this, P hat. Because we already know that this U corresponds say the field of rational functions on U is L, an extension of K, that is the field of rational functions on our base curve C. And now this L corresponds to a projective curve. Oh, sorry. Well, corresponds to a curve. We don't know yet that it's projective, but corresponds to some curve S that is the set of all DVRs in L. Okay, and then we do have here we have a field K, here we have field L, and here also L. So our morphism from K to L gives rise to the desired morphism P hat from S to C. Okay, and then by the evaluative criterion, we know that C is proper, and in particular, it is separable. Okay, so very good. We know it's proper. Now we're going to prove that it is project.
Комплит и проб одно и то же?
Yes. Sorry. Excuse me. So it is projected just by Joe lemma. We take a projective approximation. So we have some variety, let's say X. Inside we have U. So that this X is projective. U is an open subvariety, and we have projection from U birational to C. Okay, this is just Joe lemma. Since it's birational, we know that U is also a curve. Okay, and X, it's also one-dimensional, and X is also one-dimensional. So X is a projective curve. Projective curve, and by a lemma from last Thursday, our morphism P is an open embedding and extends. I mean, since our curve C is smooth, yeah, then any morphism from any curve to a smooth curve must be an open embedding, and so it extends to P hat from X to C. So this is also an open embedding. But since X is projective, then the image must be closed. And hence P must be an isomorphism, and hence C is projective.
Вот в этом месте изоморфизме важна проективность теоремы.
So now we proved that C is projective. That this curve that consists of all the possible DVRs really is projective.
Все, понял, спасибо.
Now we finally proved it. So we're almost done. And the last step is that if we have any curve S with the same field of fractions, okay, then we have an open embedding from S into C. And we have to check that the complement C without the image of S is finite.
Для чего вот это нужно последнее доказывать?
Well, we why do I have to prove it? Well, maybe this is point 3, right? I claim that any smooth curve S with the same field of fraction is an open subcurve, and this means, by definition, that the complement is finite, right? By definition of Zariski topology.
Спасибо.
Check this. Okay. So let's take non-constant function. T in regular function on S, and then the complement C without the image of this embedding is contained in the set of points such that this this function T is not contained in the corresponding DVR. Okay, because
I'm sorry. Why such T exists? What if our KFS is only constants?
Maybe you see, we can so we're proving that the complement of S is finite. So if we take smaller s, it is still fine. Yeah, if we prove that the complement to some smaller s is finite, we will be done, right? And then let's take for this smaller s a finite open and a fine open subset.
I see. Thank
and then necessarily there will be
I see.
regular non-constant function. So where do I write this? To make sure such T exists, we replace S by an open affine subset. Okay. So now the complement consists of those DVRs that do not contain this regular function T, and this subset can be rewritten as follows. They are such DVRs that the inverse function is in the corresponding is in this ring, and moreover equals 0.
Почему оно равно нулю?
What do you mean?
Ну вот t минус 1 c равно нулю. Откуда следует?
Because otherwise it's invertible, right? If it's not 0, then it's invertible.
Спасибо.
So I mean, it is equivalent to the property that T inverse lies in the maximal ideal of this DVR. Okay. Fine. So now this set is clearly finite because the set of zeros of a regular function is finite. Of non-constant function. Okay, so now the theorem is proved, and maybe let me make a few comments about this theorem. Remark. So First of all, that the DVRs like this, a DVR R C inside our field of fractions is the same as a so-called valuation on K. Namely, it's called VC from the homomorphism from multiply group to the integers. And namely, VC of any function is the order of vanishing at the point C. Okay, I mean, if it has a pole, then it will be negative. Like V0 of t is 1, and V0 of t negative cube is negative 3. Okay, but also on the projected line, say V infinity of t is negative 1, and V infinity of t negative cube is 3. But say V1 of t is 0, because at the point 1, the coordinate t does not have 0 nor pole. Okay, and we don't consider all the possible homomorphisms, but only the ones satisfying the triangle inequality, or non-Archimedean triangle inequality. So a valuation of f, or maybe plus g for two functions, is exactly the minimum of valuations of f and valuation of g. Right? For example, if one of them had a negative valuation, that is, had a pole, but other had a positive valuation, so it was regular, then if you add a regular function g to a function f with a pole, you will still have the pole of the same order as f had, right?
Should we have inequality here?
Yeah. Right. Right. It can be bigger, yeah? If they coincide, yeah. So maybe I should add
Что-то звук залипать стал.
G of f plus G. Sorry, can you hear me now? No?
Вот сейчас нормально слышно.
Okay. Sorry about this. So Altan was absolutely right. If they have the same valuation, then after you add them, you might have some cancellations, and the order of 0 can go up. But otherwise, it will be exactly the minimal valuation. So this is the definition of valuations, and then the claim I'm making is that there is a bijection between all the DVRs. I mean, such the fraction field of R is K. So this is in bijection with valuations, with such non-Archimedean valuations. And the bijection is very clear, namely given given evaluation V, then you can take the corresponding DVR as the set of all functions such that their evaluation is non-negative. And conversely, given R, you choose a uniformizer pi in the maximal ideal of this DVR, and set V of f is n, such that pi to the negative n f is a unit. So it lies in R, but not in the maximal ideal. Okay, and you know that it always exists. So we could equivalently describe our curve as the set of all valuations. Okay, and then the second remark is that now we're very close to schemes, and just replace our field K by the field of rational numbers. Okay, and then apply just the same construction. So we will have the set of all valuations V from rational numbers to integers, and there's the same as DVRs. And we know what is this. This is just 2, 3, 5, 7, 11, and so on. Just all the prime numbers. Okay, and we have the same stupid Zariski topology. All the closed sets are just finite, and the structure sheaf OC of U is just the intersection over all points in this open subset of the corresponding valuation rings. Okay, so in other words, this is the set of rational functions, rational numbers now, the A and Q, whose denominator is well divisible only by primes out of U. Okay.
Можете, как устроено здесь открытое множество? Пример.
The open sets are always complements to finite subsets. Yeah, this is the stupid Zariski topology for curves. The closed sets are finite sets.
But we again exclude the Archimedean valuation, yes? So
we did, yeah. For one thing, our valuations are supposed to have image in Z, not in R. But for Archimedean evaluation, the image will be in R. And also, I said that it's explicitly said that they are non-Archimedean. Okay, and in DVRs also for the Archimedean evaluation, there will be no related DVR. Okay, so this is a ringed space and it's called the spectrum of integers, spectrum Z, and this is very similar to what we studied before. The only difference is that the structure sheaf does not consist of functions. Let's see. Well, I mean, with a real, how to say, with actual curves, is that the sections of the structure sheaf are not functions. Yeah, I mean, well, they are rational numbers, but you cannot view rational numbers as functions on anything. Somehow, there is no base field small k where all these functions assume values. Yeah, but if you somehow agree to disregard this as an well, if you agree that this is not an issue, then it's fine. And this is what the scheme theory is about. Yeah, they are ring spaces with very similar properties. The only, so to say, drawback is that you cannot think of them as functions. But then it appears that it doesn't matter. You cannot think of them as functions, but never mind. It poses no problems. You can work with them just as with the algebraic varieties we worked with so far. Just don't think of the sections of structure sheaf as functions. You don't need to. If you go over what we studied so far, you never really need to assume that they are functions to somewhere. Okay, and now the third remark is that nothing like this works in higher dimension. Unfortunately, so already for surfaces we have, say, P2, but we also have a blow up at some point, or if you want, you may consider A2 inside here and blow up at 0 of A2. Okay, and then the field of rational functions, okay, of P2 is just rational functions in two variables, or maybe T1, T2, and it is the same as the field of rational functions on the blow up. So you see, there are rational, birational isomorphisms that are not really regular isomorphisms. For curves, it was impossible. Yeah, if you had two projective curves that were birationally isomorphic, they had to be isomorphic, and it's not true for surfaces and in higher dimension. Okay, and then if you consider valuation on such a field of higher dimension, higher transcendence degree, then they can be given by irreducible divisors, just as before, right? Given a point at a curve, the valuation was the order of vanishing of a function along this point, at this point. And now given a divisor in a surface, you can consider valuation that is the order of vanishing of a rational function along this particular divisor. Okay, so there are very many of them, but which is worse, you can also consider the blown up surface, and there you can take also a divisor, like the exceptional divisor in the blow up. It will also give rise to valuation, and then it can blow up further on at some points of this singular exceptional divisor, and you will get more and more and more valuations. Okay, in what we're speaking about, yeah, in P2 or in any iterated blow up of P2. Okay, so there is a very interesting theory of valuations, but it is somewhat wild. There are many more valuations that you can originally imagine in a higher dimension. But in dimension 1, all the valuations are just points of the projective curve, the smooth projective curve. Okay, so far so good. Let's prove one more lemma, and then go on with studying sheaves on curve, coherent sheaves. So the lemma says that if so, it sort of converts to what we just used. If there is a non-constant function f on our curve, a regular non-constant function on our curve, then our curve is affine. Okay. So how do we prove this? We take such a function, and we know that the field of rational functions on our curve is a finite extension over the field of rational functions on line. Maybe f is a bad name. Yeah, let me rename it to t. Okay, so just rational function is in one variable. This variable is our non-constant function. Okay, and let's define another auxiliary curve, the normalization of the projective. Oh, sorry, a fine line, the spectrum of polynomials in this variable in our extension field. Okay, then we have a morphism, an open embedding from our curve C into this normalization, and what do we know? We know that S is affine, right? Just by construction, it's normalization of a ring of functions. Yes, it's an integral closure of well, S is the spectrum of the integral closure of a polynomial ring in our field of rational functions. Okay, so it is affine, and the morphism, our embedding J is also affine. So why it is so? We know that an open embedding of algebraic curves is just a complement to finitely many points. Okay, and the question about J being an affine morphism is local, right? It's local over S.
Я забыл определение. Вот афинный морфизм — это что?
It means that the projection of sorry, the pre-image of a fine open subset in the base in S is affine.
Спасибо.
Okay, so the question is local over S, and locally you remove a point from some open subset U in S. So you take U minus U embedded in U. And this is certainly affine because you just remove zero of a function. Yeah, you can shrink capital U further on, so that U is the single unique zero of an appropriate function. Okay. Okay, so now you have a composition of two affine morphisms that is affine. So you have J from C to S, and then it goes to point, and this is affine, this is affine. So this whole thing is affine. Okay. Well, there we are. And now the new big topic is coherent sheaves. On curves.
Можно по поводу предыдущей спросить страницы? Так, что тут происходит? Здесь, вот я помню, что нормализация — это был спектр, ну, относительный спектр, да? Вот. А сейчас это...
When I say the word normalization in some field, I mean what is written here. It's the spectrum of integral closure of our ring in this field. It is the definition. And then the normalization in general was the gluing of such things, and so it was applicable not only to affine schemes, but not only to affine varieties, but arbitrary varieties.
Okay.
Спасибо. Welcome. So coherent sheaves. So first of all, we will use divisors on a curve C, are just formal integral linear combinations of points, like the sum of Ni, Ci, right? So in general, divisor is a codimension 1 subvariety, but now since dimension is 1, codimension 1 is just 0, so it's just a point. Okay, and an irreducible divisor is a point, and then arbitrary divisor is a combination of irreducible divisors like this, so just combination of points. This is also very special about curves, and you will see how it works specifically for curves.
And here is no difference between Veil divisor and Cartier divisor.
Yeah, because our curve C is supposed to be smooth. So there is no difference. So maybe let me write down what Altan says.
А вот это сложно понять, что Cartier равны Veil дивизорам. Это сложное утверждение?
No, because phi is smooth. No, it's then we also know that for smooth curves, all the local rings are UFD, unique factorization domains, and then V is Cartier. Okay, so we have this linear combination, and the degree of such a divisor by definition is the sum of coefficients, and also D is called effective if all the multiplicities are non-negative, and maybe let's prove an easy lemma that any well, maybe non-zero sheaf of fractional ideals I will recall in a moment what it means, is invertible. So when we say sheaf of fractional ideals, then it is a subsheaf of the rational functions. So we have rational functions, then we localize it to our curve. So we obtain a quasi-coherent sheaf that is very big, so to say, infinite dimensional, and it's a constant sheaf. The sections over any open subset is the same field of rational functions on our curve. Okay, and certainly it's a quasi-coherent sheaf of modules over structure sheaf. Right? And I is a submodule. Okay, and when I say that it's invertible, then it means that it is locally free of rank 1. Okay, we discussed it in November or December in some detail, but now maybe somebody forgot it. But anyway, it was a reminder, but now let's go to the actual proof. So let's take a point in our curve and localize there. Or in other words, just a stock.
Извините, а C это множество DVR, да, или это вообще какая-то произвольная кривая, или это не важно?
C is a smooth curve, not necessarily projective, but okay, well, so far it's not necessarily projective. Then soon we'll assume it's projective, but so far not necessarily. So we have the stock of this fractional ideal sheaf, and then the stock is certainly a submodule of this field of fractions. Maybe I should have said that this I is a coherent submodule. Okay, and then we know the classification of all submodules. So any OC submodule of its field of fraction is of the sort OCC times some power of uniformizer, or some n an integral power. Okay, so you see, it is necessarily and again, certainly you could have the whole field of fractions, but that will not be a coherent submodule. I mean only finally generated submodules. Finally generated. Okay, and then such a thing certainly is a free module of rank 1, right? With just with this generator, pi to the power n. Okay, so I proved that locally our fractional ideal is free of rank 1 module over the local ring of our point. So we are done. That's what we wanted to prove.
But we proved it stockwise. Maybe we wanted to cover with some open charts and prove.
Yeah, but just when you prove it over a local ring, that means exactly this, because this local ring is a union by definition. It's the co-limit of functions over smaller and smaller open neighborhoods. But every particular section lies in some global sections over some particular open neighborhood. Okay, so if I prove that some module is free over local ring, if the stock of some submodule is free over the local ring, it means that there is some neighborhood over which this sheaf of modules is free rank 1 over the corresponding sheaf of function. Okay, so that's what we know, and we also know that that there was a natural bijection between the divisors and the invertible fractional ideals. Namely, D went to OC of D. Okay, and once again, in our case of curves, this invertible comes for free. Any fractional ideal is invertible automatically. Okay, and now let's start with arbitrary coherent sheaf. Then, as we localized the structure sheaf OC, and obtained from it this big quasi-coherent sheaf of rational functions, we can do the same with our sheaf F. Namely, we can embed it into the constant sheaf with values rational sections of F. Okay, so this is localization of the K of C module. In other words, vector space, yeah, finite dimensional vector space over this field of rational functions. As rational sections of F. And this is the co-limit of sections of F over smaller and smaller open neighborhoods. I mean, not neighborhoods, just open set. Okay.
Определение вот этого рад F.
Yes. And so this is a constant quasi-coherent sheaf. Okay. And now.
Какой у него слой в точке у этого рад?
There was some class in November when we spent maybe an hour musing about its stocks, and the stocks are, or maybe fibers. Sorry, fibers. The fibers are zero. All the stocks are the same. They are just red F, but all the fibers are zero. Okay, and all the stocks are just the same red F. Okay, and now the definition of rank of F, or maybe just generic rank of F, is the dimension of this space of rational sections over this field of rational functions. Okay, and we have this morphism from F. I wrote that it's an embedding, but it's not an embedding, not necessarily an embedding. There is a morphism from F to this localization. And there is some kernel. And there is some image also. So the kernel is called maybe Tor, the maximal torsion subsheaf. And the image is called F3. The maximal locally free quotient sheaf of F. So I have negative statements like this: 0 torsion subsheaf to F, then free quotient sheaf like this. And why is it called torsion? Just because any section maybe local section, say S of the torsion sheaf F is annihilated by a local regular function F. So it's a regular function on an appropriate neighborhood in C. Okay, and this is just by definition, because what does it mean to be in the kernel of this morphism from F to rational sections? You just tensor your sheaf F with the field of rational functions over your structure sheaf. Okay, so if anything goes to 0 by this tensoring, it exactly means that it's annihilated by some function. So it's a tautology. Okay, so well, how to say? In general, a sheaf F is called torsion if this morphism to rational sections is 0. In other words, that any section is annihilated by some local regular function. Okay, and then the support of F is a proper closed subset, so it's still smaller than the whole curve, and it's just the union of finitely many points.
То есть носитель он всегда замкнутый, да?
Yes, the support is always closed, but for torsion sheaf, it's smaller than the whole curve, so it must be finitely many points. And then the stocks F at those points are finally generated because the whole sheaf is supposed to be coherent, but they're torsion modules, so they are necessarily finite dimensional over the base field K. Maybe
Что случилось бы плохого, если бы мы не квазикогерентные, ну, не когерентные пучки рассматривали, а просто пучки? Ну, были бы бесконечно размерные, да? А что еще бы было плохо?
Well, I don't know what I don't know what to say.
Ну, то есть я имею в виду, почему мы ограничились только когерентными пучками?
Well, because we'll study them for some time, and you will see in the process you will see how we use this coherence hypothesis all the way through.
Хорошо, спасибо.
So they are finite dimensional models over the local rings. And in particular, we can define the corresponding divisor associated to this coherent torsion sheaf. It is the sum NI-CI, where NI is the dimension over the base field K of this stock vector. Okay, and there is an evident or obvious lemma that for coherent torsion sheaf F, we have first that its sections over any open set is the sum over all the points Ci in this open set of these stalks. That's evident, and the dimension over K of the global sections is the degree of the divisor we associated to F. That's also evident. And finally, F is flabby, and this is also evident. So everything is evident, and let's prove something less trivial, and then we'll have to stop, fortunately. Now let F be a torsion-free sheaf. And torsion-free means that its torsion part is zero. Okay.
А что вот это за морфизм из F в рад? Что он делает на сечениях?
We'll discuss this. Just any section goes to its restriction to the smaller and smaller and smaller open set. Yeah. In particular, if this section is supported at some points, then you take the open set that is small, that does not contain those points Ci, and the section goes to zero. Again, now I take the sheaf without torsion. Okay, so the torsion part is zero. It's opposite to what we studied before. And then I claim that first F is locally free. Of rank equal to what I define to the generic rank. Yeah, this was the dimension over the field of rational functions of rational sections. And second, there is a filtration like this, a complete flag. Such that all the successive quotients are invertible sheaves. This means locally free of rank 1. Okay, so let's prove this. And it suffices to prove the second part because if you have such a filtration with locally free quotients, then the whole thing is clearly locally free as well. And you can find the number of successive quotients just by restricting to the generic point, to the intersection of those open sets, and there is just the usual rank, the dimension of the space of rational section. So we'll prove this by induction. in the generic rank of F. And how do we prove this? We choose a line L in this space of rational functions.
Что такое прямая в пространстве функции?
Well, this is a vector space over the field of rational functions of some dimension R, right? This R is just the rank of F by definition. It's a finite dimensional vector space. In this finite dimensional vector space, we take a line, one dimensional vector subspace, and set F1 is the intersection of this line, but localized. So it's again a constant quasi-coherent sheaf over our curve C, and we intersect with our torsion-free sheaf F. Okay.
А вот это R маленькое, оно совпадает с рангом F?
Yeah, just by definition. This by definition, small r is the rank of F. This is just definition. Okay.
Ну, просто мы вводили другое определение ранг F как размерность КЦ рад F.
As which dimension?
Вот на предыдущей странице в пункте 1 было определение, вот в самом низу, вот ранг F равно... Так, вот в самом низу, в пункте 1, ранг F равно...
Just this dimension over K of C of the rate F. So this just is. Yeah. So we consider this sheaf F1, and it has rank F1 is 1 by definition, and F1 is embedded into L tilde, into this localization, but L tilde was just L was a one-dimensional space, so L was isomorphic to K of C itself. Okay, so L tilde is isomorphic to the localization of K of C, and so F1 in L tilde is isomorphic to a fractional ideal, and we proved before that it's invertible, necessarily invertible fractional ideal. And so it means that it's locally free of rank 1. Okay, and now continue by induction. So this was one step, and now we replace our F by the quotient F by F1. So it's still torsion free. And the rank of this thing is the rank of F minus 1. So we can proceed by induction. That's it. And geometrically, maybe just let me say one last word. Any vector bundle V on a smooth curve C admits a complete flag of vector subbundles. So there will be a one-dimensional line subbundle, then some two-dimensional, and so on. R minus one dimensional. Like that. And this is a very useful fact, and not very trivial. If you have such a problem in home assignment, maybe you wouldn't know how to solve it. Okay, so that's it for today. Thank you. Again, sorry for being late. And for... Yes.
Как мы ввели L тильда? Как мы из L получили L тильда?
By the method of localization.
Спасибо.
Welcome. Any other questions?
Yeah, I also have a question. I think on page 7 we had a lemma about fractional ideals and that they are invertible. And
yes.
Does this lemma hold in general for arbitrary varieties?
No, absolutely no. Certainly not. Just for a smooth surface like A2, consider the sheaf of ideals. That is just the sheaf of ideals of the origin. Then it's not invertible at the origin. I mean, away from the origin, it's just the structure sheaf. But at the origin, unfortunately, it has two generators, the coordinates x1 and x2. So it's not invertible.
Okay, thank you.
Welcome.
А можно спросить про DVR?
Yes.
Ну, я знаю только определение через вычисление, вот которое вы сегодня сказали. И как из этого определения увидеть, что...
Which definition, which calculation? What do you mean? I don't understand.
Ну, определение DVR через вычисление. Вот эти valuation.
What does it mean by calculation? I don't understand what you say.
Сейчас. Ну, значит, вопрос, как увидеть, как понять, что между DVR и полем рациональных функций нет никаких других колец.
Well, just because in this DVR you have the maximal ideal. It is generated by some uniformizer pi, and everything out of this maximal ideal is invertible, right? And so in the field of fractions, it suffices to invert just this uniformizer pi. And then everything in the field of fractions is of the type pi to some power times unit. So there's no room for anything else. Just units times integral powers of the uniformizer.
Ну вот, если воспользоваться соответствием DVR и вычисления, valuation.
Valuations. Okay.
Ну, я не знаю, как по... Мне казалось, что вычисление это называется.
Maybe нормирование.
Да, действительно. Вот.
Yes.
Значит, вот через вот это определение понять, что нету других колец между DVR и полем рациональных функций.
Field of transcendence degree 1. Yeah, I don't understand the question. It's some specific property of fields of transcendence degree 1.
По соображениям размерности, значит.
So to say, yeah.
Хорошо.
Okay. So then let me stop the recording.